All right, we are still going through chapter 5. We move on to 5.5 at this point. And so we are graphing the other trig functions here. So we're going to look at the tangent function for quite a while. The properties of it, the graph of it here, because really sine, cosine, and tangent are sort of the more important graphs. And then we're going to sort of quickly run through the cosecant, secant, and the cotangent graphs, which really aren't used that often. But we should still at least sort of look at them. So a few things here, and again we kind of we're going to take a look at the graph. Once you see the graph of it, then you'll sort of be able to see it a little better here. But here are three sort of major significant things in regards to the tangent function. The tangent function has a period of pi instead of 2 pi. Also, the tangent function has zeros when sine is equal to 0. So at pi over 2, negative or positive, negative positive 3 pi over 2, negative positive 5 pi over 2. And this whole concept of amplitude. The tangent function does not have an amplitude. There are no minimum or maximum y values. All right, next we just take a look at the property. What is the tangent function? Just to remind ourselves, the tangent function is actually a ratio of the y and the x coordinates. So because of that, before we really get to the graph of this guy, we're going to take a look at one extra little thing here. If the tangent function is actually a ratio between the y and the x coordinates, if you think about this here, if we make a dot here, we call it the vertex, and this is 0, 0, and we have a dot here in space called xy, really what we just figured out is we just figured out the slope of a line that goes through the origin. And that's very important, especially later on when you guys are going to go into different types of equations here. So the tangent function gives us the slope of a line that goes through the origin, and that's what this says right here. So the slope function of the line OP is given by the tangent of the angle there. So let's do just one example with it. So let's take a look at the example problem before we get going here. So let's say a line L makes an angle 60 degrees with the positive x-axis and passes through the point 75. So if that is the case, can we find the equation of this line? And so what we do, all we really have to do is we have to get these points here, and then we have to get our slope. And if you remember from algebra, do you remember the point slope form from algebra? Remember this y minus y1 equals m x minus x1. And so we got it. As long as we can put in the points here. So this guy will be the 5 that we put in. This guy will be the 7 that we put in. And this is going to be the tangent of 60 degrees as given there. So if we do that, we calculate the tangent of 60 degrees, which is square root of 3, and we go from there. So notice we're plugging in the values, and then all we got to do here, distribute the square root of 3, distribute our slope, add 5 to it, and there it is. There's my, looks kind of weird though, right? Because there's my slope here. This is y equals mx plus, and there's my b value. You can't put the 5 and the 7 root 3 together because those are not like terms, so we sort of keep them separate. But this whole thing is the b value. All right, let's try ours. So can we repeat this given the fact that an angle is 30 degrees, and now it goes to the point 2, 3. All right, first things first, we have to calculate what is tangent of 30 degrees. But if we want to make a little demo, this is where we're at here. We're at a graph of it here. So 2, 3. The line that is going to go through the origin here, we're going to make the equation of that line right there. All right, so tangent of 30 degrees. Calculate that if you need to here. It's going to be, I think it's going to be 1 over root 3. And of course can't keep that as an irrational on the bottom here, so let's multiply that by root 3 over root 3, and gives us square root 3 over 3. Got it. So there's my slope. And once I get my slope, and I already have my 2 points, I can plug into this formula right here. So let's go for it. Plugging in the y is equal to 3. There's my slope, and plugging in the 2 for the x, or x1 technically. At this point, we have ourselves the form, the point slope form. Now let's just solve for y. So we're going to distribute the square root of 3 over 3 here, distribute the square root of 3 over 3 here, and we get ourselves that equation right there. And one little final step, let's add 3 to both sides. And we have ourselves the final answer. There it is. Y is equal to square root of 3 over 3x. There's my slope right here. Plus, and even though the example problem puts in parentheses, normally we don't put it in parentheses. We just know that this whole thing is the b value right there. So that's kind of cool. I've just made an equation. All right, so now let's take a look at the tangent function. How does the tangent function, if we take the unit circle approach, we calculate each one of these here at the unit circle, and then we're going to graph the tangent function. So what does a tangent function look like? So let's pick, instead of those two, let's pick the tangent function, and we're going to start it. So again, remember, the tangent function is the ratio of the y-coordinate to the x-coordinate. So notice over here as the y-coordinates gets smaller, I'm sorry, the y-coordinate gets bigger here, the x-coordinate gets smaller. So what does a graph look like? It goes like this. It goes off to positive infinity, then it goes off negative infinity. So again, we have to understand that really what you're looking at is you're looking at the ratio. So at 45 degrees, right here, that ratio is exactly even. So at 45 degrees, or pi over 4, pi over 4 should be exactly at 1, because it should be square root of 2 over 2 and another square root of 2 over 2. Okay, as you get closer and closer to 90 degrees or pi over 2, notice up here, the y value is almost at 1, but the x value gets smaller and smaller as you come here. So as you get closer and closer to pi over 2 or 90 degrees, this thing shoots up higher and higher because your denominator is so small. And so it goes off to infinity. So this little part right here has to be vertical asymptotes. There's your vertical asymptote right here. And then there's another vertical asymptote here. All right, so let's see how the graph puts this function. So let's review those properties that we had before on the previous slide here. So does tangent have a period of pi? It sure does. Notice it starts repeating itself. So from negative pi over 2 to pi over 2, once this is done, it's going to repeat itself again and again. So instead of having 2 pi as the period, like for sine and cosine, now we have 2 pi. Now we just have pi. Okay, tangent has vertical asymptotes at pi over 2, 3 pi over 2, and forever going this way, negative pi over 2, negative 3 pi over 2 going this way, and then forever. And the third option, the third the third property that we notice is that it does not have an amplitude. There's never a high point for the y value, there's never a low point, because it goes off to positive infinity and it also goes off to negative infinity. So no amplitude for tangent. All right, let's move off to the graph then. How we're going to graph this here, first an example, then we'll get started here. Let's see, how do we graph this right here? Y equals 3 tangent of 2x minus pi over 2. Well, as we learned in the previous section, what we have to do is we have to factor this 2 out. So we've got to do that step first. Factor the 2 out. And then as we do that, this should be x minus pi over 4 at this point. Okay, once we do that, we know our values. Remember that the a is the number in front of your trig function, b is your multiplier, and c is the one over here. And we're missing d for right now. That's the vertical shift here. So we don't call this an amplitude, we just call it a. And really what we're going to call it, we're just going to call it a vertical stretch. So we have a vertical stretch of 3. The period is going to be pi this time. Instead of 2 pi, it's going to be pi divided by that b value. So pi divided by 2 is pi over 2. And they will also have a phase shift. Again, phase shift is going to be this little piece right here. It's opposite. So it's the negative of negative pi over 4 or pi over 4. Okay, let's see the graph here. The new step that we do with tangent that we don't do with sine and cosine is this whole concept of locating asymptotes. Because once we locate the asymptotes, perfect, we know how this graph is going to go. So what we do is we set that little tangent of the stuff that's inside tangent. We set this equal to a negative pi over 2. We also set equal to a positive pi over 2. And then we see what happens. Because those would be the original adjacent vertical asymptotes as we start off. So in this case, we do some work here, but you guys should be able to do this here. You're going to go multiply everything by 2, and then you're going to add pi over 4 to it, and you're going to get a value of x equals 0. You're going to go on this side here, again, multiply everything by 2. You're going to add pi over 4 to it, and you're going to get a value of pi over 2. Well, what that's going to happen is that's going to really give us our interval. Our interval is from 0 to pi over 2. Those are our vertical asymptotes. And once we got that, we can graph the rest of it. So notice what we do here. It doesn't show it here, but there's a vertical asymptote coming down straight right here. There's my first vertical asymptote is at 0. My next vertical asymptote is at pi over 2. If that's the case, the middle point right here is going to be my 0. And then in between here, which would be the middle between here, this is almost in a sense almost like your 45 degree. We're going to go up to 1, but because we have a vertical stretch of 3, we're going to go all the way up to 3. So we clock that point here, and then we break this up. In a sense, what we're doing is we're still breaking up into 4 pieces. The middle section is where the 0 hits, and then the lower section here, that's when it goes down, and that goes down to negative 3. Alright, so our turn. Can we graph this guy? And so we're going to look for first is a vertical stretch. Do we have a vertical stretch anywhere here? Sure do. We have a vertical stretch of 3. But as we notice, it's negative. It's not positive here. So when you see a negative, then you also know you have a reflection about the x-axis. That's the other thing that we have here. Reflection about the x-axis. Alright, time for the period. Period is going to be pi divided by this number in front of x. At this point, it's just going to be a 1. So the period is going to be a pi. And then we have ourselves our phase shift. Phase shift is going to be the opposite of the number here. So it's going to be a phase shift of a negative pi over 4. Alright, the other thing we have to do is the vertical asymptotes. So let's go for it here. So let's place everything here. So basically in a sense, it's this stuff here. It's the stuff that's inside tangent. We're going to set that equal to negative pi over 2. And if we do some work here, we'll figure what that is. We're also going to do the next one here. So we're going to place it as, let's see, we're going to subtract pi over, let's see what I did here. Hopefully you guys can do the math here behind it here. So this right here, I just brought it down, forgetting about the 1 here. Then I made common denominators here. So I just made everything with a denominator of 4. And then if I subtract pi over 4 from negative 2 pi over 4, that's going to give me a negative 3 pi over 4. So there it is. There's where my vertical asymptote is going to be. Next one, set it equal to positive pi over 2. And again, same exact process here. Drop the 1 first. Then we're going to subtract pi over 4 from pi over 2. And we're going to get an x equals pi over 4. Okay, so when we graph this, we're going to graph the vertical asymptotes first. Once we have that, pretty much we're going to think about that's vertical stretch and reflection. Alright, so let's get started here. First things first, I'm going to make my grid here. And so everything is in terms of pi over 4. So let me make everything in terms of pi over 4. So I have a pi over 4 here, 2 pi over 4 technically, 3 pi over 4. I'm going to go backwards as well, negative pi over 4, technically negative 2 pi over 4, negative 3 pi over 4. And I'm going to place my vertical asymptote at negative 3 pi over 4. The other one's going to be at a positive pi over 4. Okay, and then from here, notice it's broken up into 4 pieces. There's my 0. This is the middle, really, in a sense, between these guys. So that means my 0 is going to be right here. All right, and then again, now I've got to think about the stretch and the reflection as well. So normally the tangent function goes like this, right? It starts on the bottom, and as it works its way up to the right, it goes up to the top. But because of our reflection, the graph is going to go like this. It's going to start off high right after the vertical asymptote and come back low before the next vertical asymptote. That's what I'm looking for. And also don't forget we still have a vertical stretch of 3. So let's do this here. Let's bring it down to here. So that means if it's coming, it's going to come from high, it's going to come this way, and it's going to go low. And I'm going to put in my, since I know it's going to go up to 3, I might as well put in my dash marks for my y-axis. And then here we go. I'm going to use this pattern right here. So I'm going to start off high. That means it's going to come down. It's going to hit in between these 2 points here. I'm going to go up 1, 2, 3 and develop this dot here because it's going down. So then in between these 2 points here, the 0 and the next vertical asymptote, I'm going to go down 3 and produce this point here. And at this point, I'm good to go. I can connect the dots. And I have one full period. So the phase shift happens because I know where the vertical asymptotes are. And the period happens because I know the vertical asymptotes. So with the tangent function, notice it's a little different of how we graph it. The vertical asymptotes are the important ones. We break it up into 4 pieces, and we divided it into high, 0, low, or if it's going up, it would be a low, 0, and a high. All right, next we're going to move on to the graphs of the reciprocal functions here. So we have, and here's where things get a little bit interesting here, is this whole concept of, if we're going to graph the reciprocal function, what we should do is really just graph the function itself of the reciprocal function, and then take a look at the function itself. So let's sort of see. So we have, if f of x is the reciprocal of g of x, we have a few things we should note here. So period. So if g of x has a certain period, that means f of x will have the same period. So that means like sine of x has the same period as cosecant of x. Next are the zeros. Zeros are defined whenever The other graph has a vertical asymptote. Remember, if you take 1 over 0, it's just going to be undefined. So whenever the function itself has a 0, the reciprocal function has a vertical asymptote. Okay, even non-relationship. Okay, so if that function is odd, its reciprocal would be odd. If it's even, its reciprocal is even. All right. And then there's a few other things you can take a look at. Positive and negative values. 1 is a good one here. If one certain function has 1 as the answer, its reciprocal will also be a 1. And also negative 1 works the same way. If negative 1 is the y value, the reciprocal of negative 1 is negative 1. So the reciprocal functions and the original functions will have two numbers in common. 1 would be one of those, and negative 1 would be the other. All right. Next is this whole concept of if f of x is greater than 0, the sign here, that means the reciprocal function will be greater than 0. If it's below 0, the reciprocal function will be negative as well. And then there's a relationship between increasing and decreasing. That is actually a different relationship here. It says if g of x is increasing, f of x will be decreasing. So they have a opposite relationship here. And we'll see those as we graph these here. All right, and next, magnitude. If the absolute value of g of x is small, then the absolute value of f of x is large. So the smaller the number for the original function, the larger the reciprocal function. All right, and again, this is as especially when you have numbers approaching 0, but we'll see those as we take a look at the original functions here. So let's take a look at the cosecant function first. So the first thing we should know is, hey, you know what? Cosecant function is the reciprocal of the sine function. So when we do this here, what we want to do is really, in a sense, just graph the sine function, and then we'll sort of jump to the cosecant function. All right, what does the graph look like? And notice a few things here. If we were to graph the sine function, here's what we're going to get to here. This is hopefully will explain all those properties here. Here in black, this is the sine function from 0 to 2 pi. Notice what's going to happen is the cosecant function, whenever you have zeros for the sine function, the cosecant function is going to have vertical asymptotes right here. Next, whenever the sine function reaches a 1, the reciprocal of 1 is 1, so therefore this is the point of contact that's going to happen between the sine function and the cosecant function. The other point of contact is at negative 1, because again the reciprocal of negative 1 is still negative 1. All right, as the sine value is very small, notice the cosecant value is very large. Also notice when the sine function is increasing, the cosecant function is decreasing up until this little plate right here. As the sine function decreases, the cosecant function increases until you get to 0. Or right before 0, the number is very small, so that means the reciprocal value is going to be very high. Okay, as it goes to the negative territory, it starts off, the cosecant function starts off very largely negative. And again, as the sine function is decreasing, the cosecant function is increasing up to negative 1. As the sine function increases, this starts to decrease. So again, it's one of those where a picture is worth 1,000 words over here. All right, let's also take a look at the secant function. Again, secant is the reciprocal of cosine. You can take a look at all these things right over here, but it's probably better just to take a look at a graph. So the cosine function, remember it starts off at positive 1, goes all the way down to negative 1, and then goes all the way back up to 1. So the black curve is the cosine function, and notice again the secant function is going to make contact with the cosine function at that point there. When cosine hits a 0, that's going to be the vertical asymptotes. again, each time cosine equals 0, that's going to be the vertical asymptotes. Okay, so what are we really trying to do? What we really want to do is to graph the secant and the cosecant functions in terms of sine and cosine. And if we can do that, we got ourselves everything we need here. Also what it is, I have this little thing called OOO. All this is mean just out of order. We're going to do practice problem number 4 first, because it deals with the secant function. Then we're going to talk about the cotangent function, and then we're going to graph it later. But I think the book was sort of off sequence here. All right, let's go for it here. What we should do is think about, in a sense, almost like graphing a cosine function here, since secant is reciprocal of cosine. Let's do this here. Let's think about if this was a cosine function. What would be happening here? So first amplitude would be 2. And then we have the period. So the period would be, it would be 2 pi divided by 3, that little value right there. There's my period. So I start off drawing this out. We need 2 intervals here, so I'm going to double this right here. So 2 pi over 3 times 2, that gets me all the way to 4 pi over 3. But let's take a look at the cycles. If 2 cycles, one period is 2 pi over 3, and that means 2 cycles will be 4 pi over 3. That's what I wanted to do here. All right, 2 pi over 3 graphed. Half of that would be 2 pi over 3. Half of that would be pi over 3. Okay, remember this is 2 cycles though. So I want to really break this up into 4 pieces. That's what I really want to do here. Break that up into 4 pieces. So there's my 4 pieces for the first cycle. And there's my 4 pieces for my second cycle. All right, and then let's do this here. Let's put in all the values for the cosine function. Not all the values, but at least the critical values here. So we know we're going to go all the way up to 2, down to -2. And here it is. Cosine is 1 at 0, goes down to -1, comes back up to +1 in the set that I want it to be in, 2 pi over 3. Then I'm going to go down again to -1, come back up to +1. There it is. I have 2 cycles of cosine, and of course that's not what I'm trying to draw. I'm trying to draw secant. So now let's change these up. Whenever you see zeros, those become our vertical asymptotes. So at pi over 6, pi over 2, 5 pi over 6, 7 pi over 6. Perfect, that works. Now the things that they're going to have in common are 1s and -1s. And you sort of have to know how the cosine graph looks like without really graphing it here. So now let's do this here. Let's see. Down at the bottom, again, because it's a -1 transition, you know it has to go like this here. Because it's a +1, they touch right here, and again, it's always a sort of U shape, just kind of depending where it's at. The next one. And this one, we're not going to do the full one because our graph starts at 4 pi over 3. So we're going to just go to the red dot right here, and that'll be good enough. And then, of course, we have the beginning one that we didn't do yet. So it starts off here and moves up. Now, can you scoot back just a little bit and do this one? Absolutely. But remember, we were given 2 period intervals to graph, but we did them. This is 2 different intervals. Starts off at 1 goes up, comes from the bottom, comes back down, and again, right here would be 1 full period for secant. Then you have another one starting here. Notice that this right here matches up with this one here. So there's your match. There's the match from the bottom, and then again there's the match from the top. Some properties here that you may want to read through. Maybe take a look at your piece of paper to see where things are here. So again, cosecant and secant both have periods of 2 pi. The domain is all real number except for those vertical asymptotes. So except integer multiples of pi, except odd multiples of pi over 2. Range, notice there's nothing in the middle. They go from negative infinity because they're way up high. I'm sorry, negative infinity to negative 1 because they're low, and then you have this little space in between which they never touch. So they don't ever touch an x-axis. Right? They start off back at 1, goes off to infinity. Same thing for secant. Vertical asymptotes, again, this should match with the domain. X-intercepts, like we said, no x-intercepts for either one of them. They don't come close to that. All right, and symmetry, because sine is an odd function, of course. There you should see odd. This would be a cosecant is an odd function. They should have symmetry about the origin. Since cosine is even function, secant is also an even function. And again, as you graph these, you should see y-axis symmetry. So you should be able to fold this along the y-axis, and they should be the same. Now let's move on to the cotangent function. Cotangent function is similar to the tangent function. It has the same period as the tangent function. And again, all the times where tangent is going to be 0, we have ourselves vertical asymptotes. A few things here. Both functions are odd. Makes sense. There's the reciprocal relationship. And they will have the same sign. So if tangent is positive, cotangent will be positive as well. So what does a graph look like? Notice for the tangent function, remember start off with 0, 0 here, and the tangent function goes like this. So in this case, that 0 really translates into vertical asymptote. And then, they should, I'm not sure if there's, they should put dashed lines coming down this, because there is a vertical asymptote right on the y-axis. All right, let's look at an example before we look at, before we start to graph the cotangent function ourselves here. So we have -4 cotangent of x minus pi over 2. Okay, so again, just like the cotangent, just like the tangent function, we define our a value, define our b value, and we define our c value, or the opposite of the c value, because of the formula. Vertical stretch factor, because negative, we have ourselves a reflection about the x-axis. Period is going to be pi divided by 1, because that's the b value. And we got a phase shift, which is the c value itself. What we do is now we locate the two adjacent asymptotes. The first one occurs at 0, the second one occurs at pi, originally from the graph that we just saw. And what we do is we add pi over 2. So again, our new one is at pi over 2. Add pi over 2 here gives you 3 pi over 2. So again, the interval that we have to complete a full cycle is from pi over 2 to 3 pi over 2, has a length of pi. Then the book shows you these values to continue this whole vertical asymptotes. If you want to, that's fine, but I usually don't do that. By the time you set your vertical asymptotes up and you know where your zeros are, you got yourself a graph anyways. Here it is again, just too many steps really to do when you really don't need to. Okay, and the graph, here it is. So we got vertical asymptote pi over 2. Also a vertical asymptote of 3 pi over 2. So here it is, we got this right here. And then you know that in the middle of it all, it's going to hit a 0 value right here. Cotangent usually comes down and like this. But instead, because we have that reflection about the x-axis, now it's going to be going up just like tangent. It's going to be up like this here. So again, in between pi and 3 pi over 2, it has a vertical stretch of 4 going up, and between pi over 2 and pi, and again, it has a vertical stretch going down of -4, and there it is. So we graph this line first, and then we can graph as many pieces as we need to from then on. All right, now we're ready for practice problem number 3. We're going to graph this. We're going to graph -3 cotangent of x plus pi over 4. I'm going to take a look at that. I know I am going to change something out right here. Let's see, for some reason they have a k over here. Shouldn't be a k, it should be a c. We like a c value right here. And I'm going to do it again, because it did it again. Right there, c value. Okay, cool. Now we're ready for practice problem number 3. So first things first, vertical stretch of 3 for the previous problem. Do we have a reflection about the x-axis? Sure do, because we have ourselves a -3 originally. What's the period? Period is going to be a pi, because the b value is technically a 1. And do we have a phase shift? Yes, we do. It's inside the function itself, it's x plus pi over 4, therefore we have a phase shift of -pi over 4. Now here, it actually does tell us what interval to graph it on, so we'll have to see how that's going to work as well. All right, also the vertical asymptotes. Let's put those in here. That's my formula for vertical asymptotes. One occurs at 0, the other one occurs at pi. So plugging in the 1 for the b value, x, in a sense, plus pi over 4. The ones disappear. Subtracting pi over 4, there it is. There's my vertical asymptote. Next one, plug it in the b and the c. Get rid of the 1 there. Subtracting pi over 4 from pi should give us a 3 pi over 4. And I think we're ready. Of course, we're going to start off with the vertical asymptotes first, and then sort of put in the rest of these right here. So here we go with the graph. It told us in the problem itself we have to graph from -3 pi over 4 up to 5 pi over 4. So I guess we have ourselves our tick marks for our x-axis. All right, with that, also we know we're going to go 3 up and 3 down, so I might as well put that in there as well. But vertical asymptotes go first, so we have one at -pi over 4. We have another one at 3 pi over 4, and since we have a denominator of 4 each time, we can kind of see if we need to put another one here. So that means there's a pi over 4 from here, another pi over 4, pi over 4, pi over 4. So there's 1, 2, 3, 4. We go over here, 1, 2. It doesn't reach. So there should have been another vertical asymptote here if we were to graph it this way. All right, next, we know that in between 1, 2, 3, 4, the middle one right here is going to have our 0, since there's no vertical shifting up or down. So now the question is, do we have so again, the cotangent function usually goes like this, right? That's the normal process of a cotangent function. And so what we have is this is the normal cotangent function. The only problem is, since we have a reflection about the x-axis, we know we're going to graph this guy. So that's what we're looking for. So in between these two here, we're going to go down 3. In between these two here at pi over 2, we're going to go up 3. And at that point, once you get those, you're ready for graphing. Good. Now the question is, you have to still graph it over to the other pieces. So once you have one full period, the rest should be pretty easy. You just move everything over. Or if you want to do it even this way here, you can say pi over 4. And we got 1, 2, 3, 4. That means I'm going to add another pi here. So pi over 4 plus pi gives you 5 pi over 4. So you know your next zero is here. Graph that, and then go backwards here. So then 1, 2, 3, 4. That's cool. That means there's a 0 right here. That means in between these two, there's the extra little 0 here. And graphing it. And that sets that whole entire graph right there. All right, just a few properties here. Again, this is in your textbook as well. Tangent and cotangent, these are the reciprocal functions here. So period is the same for both. The zeros for the tangent occur at multiples of pi over 2. The domain for the cotangent function is integer multiples, all except integer multiples of pi. The range, both the same. Vertical isotopes, odd multiples of pi over 2 for tangent, integer multiples of pi for cotangent. And again, more properties here. Do they intersect the x-axis? Yes, they do. For tangent, it's multiples of pi. Cotangent, odd multiples of pi over 2. And the symmetry, they are going to be both odd functions, since they're both reciprocal functions of each other. This one I just thought was a pretty cool example of the cosecant function. At the same time, it was a cool example altogether. Graphing a range of Mach numbers. So what in the world is a Mach number? Let's see if we can just sort of read it through here. Let's see what we get here. So when an airplane travels at supersonic or hypersonic speeds, so that means they're traveling at the speed of light or beyond, I'm sorry, not the light, at the speed of sound or beyond the speed of sound. We have small disturbances in the atmosphere are transmitted downward within a cone. So the cone intersects the ground, and the edge of the cone's intersection with the ground can be represented in the figure in the next slide. We'll see that in just a bit here. The sound waves strike the edge of the cone at a right angle. The speed of the sound wave is represented by leg S of the right triangle in the figure. So let's see if this picture is going to give us some more clue. What in the world are we talking about? So if we're talking about a jet inside here, the plane moving at a certain velocity right here is represented by the hypotenuse of the right triangle in the figure here. So again, the velocity here, and it forms a right triangle here. And right here, the speed of sound is represented by S. The velocity of the airplane is represented by V. And then we have an angle, vertex angle X right over here as well, which we'll talk about in just a bit, I think. So the Mach number, M, is given by this. So you're saying he goes Mach 3, or this airplane is going 2.4 Mach. And so what does that mean? Is the speed of the aircraft divided by the speed of the sound. And we'll get that. We really have on our hands is really, we can just look at the angle measurement divided by 2 and take cosecant of it, and that actually also will give you the Mach number. So if you can't really see the how fast the airplane is going, or you can't see the length from the cone back to the airplane, that's kind of hard to see. But sometimes you can figure out the angle. It's really easy to see the angle in these. All right. Okay, so what do we have here? Is we have cosecant of x over 2 is equal to, again, this is going to be, we like these better. And so what we'll do is we graph a sine of x over 2. And if we do that, notice it's our angle measurement right over here, right? It's the multiplier to our period. So that means for pi, instead of going, let's see, all the way up, all the way down, and getting back to 0 by 2 pi. What we've done, because our period now is 4 pi. So this is the sine curve. That black one right here is a sine curve right here, the black curve. Okay, but the cosecant is going to go like this, right here. So in our problem, graph the Mach number function f of x at the angle of the vertex of the cone varies. What is the range of the Mach number associated with the interval from pi over 4 to pi? So they're saying what interval represents Mach numbers from here to here. So as we looked at the angle measurement, we found it to be 45 degrees. And what we did is we divided that by 2, and then we took cosecant of it. The Mach number turns out to be a 2.6, so it's traveling a little bit over 2.5 times the speed of sound. That's kind of what we're looking at here. If the angle measurement is at pi, straight angle, right? That means you are traveling at the speed of sound. So it's Mach 1. So let's take a look at maybe a video. This might clarify a few things here. So that's kind of what we talked about here. So for pi over 4, we punch it in, it becomes 2.6. For pi, we punch it in, it becomes 1. So then the range for Mach numbers associated with this interval is going to be anything above Mach 1 and up to 2.6. So this is a little video showing a few airplanes getting to supersonic speed. Anyways, I thought that was kind of cool. So airplanes going beyond the speed of sound, and because of that, the little cone is formed. So notice it's kind of hard to tell the velocity of the airplane and then the right triangle measurement. It's a lot easier to look at a picture and take a look at the angle measurement of that cone that was formed. All right, for our purposes, practice problem number 5, which is the last one for us, is we have x is equal to pi over 8, and we are told to figure out looks like the range that corresponds to that. So pi over 8, all we're going to do is just plug it into a cosecant function here. So pi over 8 divided by 2 will become cosecant of pi over 16, and we're going to punch this in a calculator here, and of course the calculator does not have cosecant. So if you're going to do this, you're going to have to put it like this in for the calculator. It's 1 divided by sine of pi over 16. So first things first you got to do on the calculator is you have to go into your mode, and you got to make sure that you are in radian measurement. And make sure this is highlighted. If you have degrees that are highlighted, just kind of put your cursor, your flashing cursor over here, and then click enter, and that will highlight this. Next, let's put it in. So you're going to put it just like this. You're going to put 1 divided by sine. And once you press the sine button, a parenthesis is going to open up, and you got pi divided by 16. Close it off, and you got an answer. Answer is approximately 5.1. Next, x is equal to pi over 4. So if we do that, we're going to punch in pi over 4 divided by 2, which becomes pi over 8. Then at that point, again, can't take cosecant because not on our calculator here, so I have to convert it to sine. 1 over sine of pi over 8. Punching that in real quick here into your calculator. Again, make sure you are in radian mode. And you get like this. 1 divided by sine of pi divided by 8. And you get a 2.6, so approximately 2.6. So what is the range that corresponds to what we want to find out? So that means we go from 5.1 to 2.6. There's our range.